Alright, we're ready to begin Chapter 5. Welcome to Lake Wobegon, where all the children are above average norms and percentiles. You'll see 3 smiley face right here. And according to our author, the more smiley faces you got, the easier the chapter. I don't know if he kind of missed it, but I think I'd go with 2 smiley faces on this one because it is a tough chapter. As far as I'm concerned, maybe one of the toughest ones in the book. But we're going to study norms and percentiles, which kind of help us make comparisons between scores. How do you measure up to everybody else? Whenever we do our compass testing and our students have to make their cutoff scores, how do they measure up to everybody else that's taking the compass test at our school, in our region, maybe even at the state? You can do that with norms and percentiles. And so we're going to look at this chapter, and I think hopefully what's going to help you is to look at your table that's in your chapter 5. The author kind of gives you an example of a 20-question test and kind of builds the whole chapter off of that test to show you the concepts in this chapter, and I'm going to try to hold on to those examples just like he does as we go through this PowerPoint. So here we go on chapter 5, and I can guarantee you this is as bad as it's going to get, because the next chapter starts our focus on the test items, and so we are going to leave all of this math and statistics behind us, starting with chapter 6. So just hang in there. Things are going to get a whole lot better very, very soon. So here we go. Norms and percentiles. Now, they talk about a raw score versus an observed score. Now, according to your book, the raw score is the score you observe or the observed score. Now, that's what it is. If you make a 25 out of 30 on a quiz and your score is a 25, that's your raw score or observed score. These are the same things here. It is an untransformed score before any type of operation is performed on it. Now, what kind of operations can we perform on it? Well, we could change the score. I could decide that, well, I'm going to give everybody else 10 points. And so they make it 25, I add 10, this is 35. So now they have a higher score than the total is. Got a 30-point test, they got 35, so they got an A plus 5. So we can do things to our raw score, but it's relatively meaningless, but it provides the basis of other scores, and they give examples of standard scores and percentiles. So the raw score is what you make. It's observed. And here we have your author's example of 50 students that took a 20-item test So they had 20 questions. Let's say they were a point apiece, and you had 50 people who took it. And here are their student IDs, 1 to 50, and their names. 2 columns there full of names. And then we see their raw score. Bruce kind of barely made it on this test, but evidently Chandler must have studied the night before, and so he got a 20. Susan might have missed a couple of them, or 3 questions. She probably got a high B. Zachary didn't get it done. And so you see down the list, we can figure out who passed, who failed by just their raw score right there, and dividing it by the total number of points possible. So for this case, we just go 12 divided by 20. Of course, Chandler there is going to have 100% because he's got 20 out of 20. Correct. So he's got that good 100. And everybody else can figure out their scores from that point on. All right. So what does that mean? Well, obviously it just means that some students got more right than others. Does it mean that somebody's smarter than somebody else? Does it mean that somebody studied and somebody didn't? We can draw some inferences from this, these scores. But pretty much all we've got right now to work with is just raw scores down this column and this column. And that's all they are right now. So let's take a look at the next slide. Now, we talk about 2 types of scores. First, the norm reference scores. And we have 3 different types of scores under the norm reference, and then the criterion reference scores, which is, we only have 1 type right there. And so let's look at norm reference scores in general. Norm reference scores are used to evaluate one's relative performance and for us to be able to compare somebody's scores to others. And remember, relative performance. How do you compare to others in your group? And so we have a set of norms. It's a set of scores that represent a collection of individual scores. In this particular case, we would have a collection of 50 scores. For that particular little example we've got, 50 people took the test, we've got 50 different sets of scores. Now obviously some scores are the same as others, but every person has a score. Now, what's so important about norms? Well, they're valuable in allowing for the comparisons of outcomes with others in the same test taker group. All right? That group of 50 people, we can allow us to make comparisons based on those 50 sets of scores. Now there are some ways that we can do that to be able to make those comparisons, and we can take the raw score, the number of points they got out of 20, and convert them into percentile rank, Stanine scores, a z-score, or a t-score. So there's like 4 different ways that you and I can take this raw score and convert it into something we can use. So let's take a look at them. The first is percentile rank. If you have any kids in school or grandkids, they'll take some tests, and then you'll get some test results, and they'll tell you your child scored in the 88th percentile group, or they scored in the 65th percentile. What does that mean? What difference does that make? Well, let's take a look at what percentile is. It's a point in a distribution of scores below which a given percentage of scores fall. Just for example, somebody is in the 45th percentile. And this is just another way to write it. Don't get upset about this. This means percentile, and we're talking about the 45th percentile. And that means it's the score below which 45% of the other scores fall. So what does that mean? If we can convert all of those scores, and let's say I took the test and I fall at the 45% percentile, that means 45% of the other scores of all the people who took the test are below me. So I'm not really in that big of a group. And so if somebody took the test and they are in the 80th percentile, that means that 80% of the scores fall below them. And so you can kind of see, the lower the percentile, kind of the lower, as the second bullet says, the lower a person's rank within the group. So if I'm at the 45th percentile, I didn't do too good, because only 45% of the group, less than half of the group, did worse than me. And so you want to be in the higher number of the percentile group, and this number can be anything from 1 to 100 or 99 right here. But last but not least, and very important, it tells us nothing about the absolute performance of what that student did. All it tells us is their rank in the group. That's it. Now, there's a way to compute percentile scores. And so, we can do that very easily. It's your percentile group, and the R could be, like I said, be anything between 1 and 99. B stands for the number of observations with a lower value, and N is the total observations. So, getting back to our example, let's say we want to figure out the 30th percentile. And just for example, let's say that score was a 9. There were only 9 observations with lower values from what I made on the test. Only 9 people scored worse than I did on that quiz. And of course, the number of observations would be what? Right, 50. Because 50 people took the test. We've got 50 different sets of scores. And so we divide 9 by 50, and that would be our percentile. So, and then of course, that would be times 100. So you'd have a decimal here, and what you'll wind up with is a percentage whenever the calculations are all done. So that is percentile. And look now at what they've done to the little table here. We still got our 50 people, but now we went ahead and ranked all the scores from highest to lowest. Chandler and Rochelle did a good job. They got 20s. They got them all right. But then we got a whole group of 19s. All these people did was miss one. Then we got one person that just missed two. Well, Stu there just was one short of getting an A maybe. Then we got a number of them that got 17s. Got a few 16s. A few 15s. Some 14s. One 13. Keith made a 13. Number of 12s. Number of 11s. A few 9s. Some 8s. A couple of 7s. 3 6s. And then this last group right here, well, they're bringing up the rear. But we can come back and look at everybody's score and then see how many of them fall below. Now, we have some different percentiles. The 50th percentile is the middle or median score. So we've got 50 scores. Halfway would be 25. So we look at what score is, and I'm going to go ahead and go back. We look at what score would be halfway, and so we just go right down the line. This is, we got 25 in each column. 14 would be your median score right here. Kind of see that? You count from the top, work your way down halfway, which would be 25. That is the middle score. It's that simple. Then we've got what is called the 25th percentile, or Q1, or quartile 1, or quarter 1. Remember, quartile means 4, so we're going to look at 4 different we're going to divide all these scores into 4 parts. So from the 20, we would start with the 25th percentile, then go to the 50th, and then to the 75th percentile. And so we have quartile 1, quartile 3. And so we just pretty much divide all of the scores into 4 equal sections. So 50 divided by 4, we divide that out, and then we look at our scores and just divide them up like that. Dectiles, or I guess that's how you pronounce it. Dec means 10. And so all we're doing now, your scores are divided into 10 equal parts. So in this case, we've got 50. We divide it by 10, that's 5. So every 5 scores is going to give us a decile. And here's your example on table 5.3. Now you don't see it all here, but I'm going to go ahead and go through the columns so you look at your examples. Whoops. Here we go. From the percentiles, notice how we go from first all the way down to 100, huh? See how that goes? Because a percentage is some part of 100. Now notice how from there you look at the quartile. Your quartile, the first quartile goes from your first percentile all the way down to 25. Then it picks up from 25 to 50. That starts your third quartile. Then your third quartile goes from 75, and then from your fourth quartile is from 75 to 100. But now look at your decile. 1 through 10. Second decile, 10 to 20. Third decile, 21 to 30. Fourth decile, 31 to 40. And so forth and so on. See how that works? You're taking all of your percentiles and dividing them up into 10 parts. And there it is. Quartiles and deciles. Now, what in the world is a Stanine? Stanine scores divide the distribution of scores into 9 equal segments or sections with a mean of 5. Now, what in the world does that mean? Alright, getting back to our table. Take all the scores. We look at the distribution of them. Remember how I kind of went through and said how many 20s we had, how many 19s, 18s, 17s, so forth and so on. That's the distribution of them. How many people made what? But you take that distribution and we divide them into 9 equal segments or sections with a mean of 5. Now, what do we mean by a mean? Well, the mean is just another name for the average. And what is an average? Well, don't we add up everything and divide by the total? Sure, that's what an average is. So if I want to find out what my average score is on those tests, what I do is I take all 50 scores, add them together, and do what? Divide by 50. And I will find my mean. Now, what's nice about Stanines, they're easy to compute. They are represented by a single digit from 1 to 9 there. Remember, they got 9 equal segments. They represent equal units along a continuum. But unfortunately, they still tell us little or nothing about the performance of our students. So let's take a look at our Stanines. Look how they're different. See how the mean here only goes from the 1st to the 5th percentile. Notice how the next one proceeds to the 10th. See how it's a little bit bigger than this one? And then look at here. The 3rd is a little bit bigger. Now remember, they only go up to 9. You see how here we only have the 9th, but look how that one is smaller compared to the others. And so there's a difference in the distribution of them. The 5th is the biggest. See right here? And so what happens if I took all those numbers and put them along a line from 1 to 100? That distribution would kind of follow a curve like this, which is called a bell curve. And so this would be 50% right here. And 5 would be like right in here. 4 and 6 would be here. 3 and 7 here. 2, 8, and then of course 9 right at the end. And this is what we call the bell curve. And it kind of sets the standard for the Steinheim scores, because the vast majority of our scores ought to lie right in here, from whatever this number right is to whatever this number right is. So the majority falls right in the middle, and then the ones who did worse and those who did better, you know, are on either side of the majority right there. So that's what a Steinheim can do for you. Standard scores. It's a score that has been standardized based on some metric or some factor, and it's usually variability. You know, how much do our scores vary? Well, there's a way that we can figure that out. One is by a z-score. It's the most frequently used, and it allows for comparisons across different distributions. Now, this little formula is on page, let me see here. I had it here, and then the book closed on me. But this formula needs to be kind of modified a little bit, and I want to kind of show you what needs to be done here. Alright, your z-scores is equal to x, and that's the value of your score. Minus, and this x ought to have a bar across it. Your book on page 95 shows you that. That bar stands for the mean. In statistics, that is the symbol for mean, which is the average, divided by a number called the standard deviation, or S, as your book says. What is standard deviation? Remember, we talked about the Steinheims. It's the amount that those scores deviate from the mean. How far off the middle score, or the average score, do those scores deviate. Plus on the high side or on the low side. And you can measure that. Alright? So z-scores help us to kind of balance scores out. And so we kind of know how much above or below the average score we are. And here's some examples here. Notice how here nobody is in any kind of order here. Here we have a minus 2.0. Here we have a plus 1.4, a plus 80. And then we have positive and negatives. Look at this score though right here. Bruce got a 12. He missed 8. Susan just missed 3. And Chandler got them all right. Notice how he has a higher z-score than all these others do. Because this one's positive, this one's positive, this one's even further because it's negative. It's on the other side of the 0. But who's got, look at the smaller numbers here. They're on the 15s, 14s. Let's find the one that had the 13. If I can go down the list here, because I think there was 113 in the group. Look at this. Keith's got a 0 z-score. What do you think that means? Keith's score was the mean. He had the average score, and so he is, we're measuring everybody's score either on the plus side or the minus side of Keith's score. Look how the 14s, a 0.2, that's pretty close, and 11 is on the back side. And to kind of use the bell curve, here's Keith's score right here. I'm going to put a K for him. Let's look at Kim. Kim's got a 16. He ought to be somewhere over here. But look at poor old Bruce. He came on the back side of that 13. So his score ought to be somewhere right here. Does that make sense? You find the average score, and then you look at everybody's score either on the back side or the front side of that middle score or average score. Chandler's going to be on the front end way out here because he got 20 right. So I hope this kind of makes sense to you. We can see kind of where the scores all fall if we would plot all of this out along this curve. But that's what standard scores can do for us. Now, normalized standard scores. Your z-score is forced into a distribution that has characteristics of a normal curve. Remember, I showed you just the curve just a minute ago, and how all your scores kind of fit from there. But then we've got what is called the t-score. It's computed from first computing the z-score, then we transform it. Now, why would we want to change it to something else? Well, look at what we got here. We got our two perfect testers here, Chandler and Rachel. They both made 20 on the test, didn't miss a one. They wind up with a z-score of 1.4, which is on the far end of that bell curve. They're way over here because they got them all right. Remember Keith there? He had a 13. That was the middle score. So they're over here with their 20. But then we take the formula where we take the z-score, multiply it by 10, and then add 50 to it. Then we come up with a score of 64. David missed one, got a z-score of 120, so he'd be right around here somewhere. But his t-score is 62. Now, what's the difference between this and this? Well, just a transformation right here with this formula. So that pretty much is what your t-score is all about. It just puts it into another set of numbers for you to compare. And so, criterion reference scores. Criterion referenced scores are scores based on a predefined set of performance criteria on which outcomes are evaluated. So if you're looking at, testing somebody, you need to know up front what kind of performance criteria you're going to evaluate those scores from. For example, let's say you're a welding instructor and you are going to give a criterion-based set of scores. I'm your welding student and you tell me to do a vertical uphill type of weld. Well, I go and do the weld. I bring it to you to get a grade on it. You look at it and say, okay, you got a 25 on that weld. Well, okay, I got a number. Did I pass it? Did I fail it? Well, is it 25 out of 100? Is it 25 out of 25? And what is it that you're grading me on? Is it whether or not the weld will hold when the pressure is applied to it? Do I get points for that? Do I get points for appearance? Do I get points for penetration? Do I get points for the width of the bead and the look of the bead and how many passes I made? There's all kind of criteria that goes into that. And so you're measuring somebody's ability based on some predetermined criteria. If you, like our truck drivers, will go out there and grade people on how they handle a truck, and they have this whole checklist that they go out there and they just are watching like hawks how they do things, and there are a predetermined number of points for everything that they are looking for. And when it's all said and done, the student has to go out there and make a certain score out of all those criteria. Now, the importance here is on performance, and that's pretty much what we're looking for our students, not on the relative position or comparison to others in the group. Here we're measuring everybody against the performance standards that we've got for you and everybody else that's being tested, not to compare whether Johnny or Sue's scores are either close are far apart from each other. So it's a whole different way of looking at scores. Are you comparing people to people or people to performance? And in vocational education, this is pretty much what we do a whole lot of the time, is our criterion reference scores. Now, another term, standard error of measurement. All right. We don't live in a perfect world, and so our tests aren't perfect. And let's face it, people aren't perfect either. But what standard error measures do for us is this. It tells us how much does a test score vary for an individual from time to time. If I get 10 students and I give them the compass test once a month for the next 5 months, and I take a look at their scores in reading, English, and math while they're taking my developmental ed courses, what would I expect the scores to look like on reading, English, and math? Well, hopefully I would like to see their scores improve. Let's say they've got a 25 in math. I'd like to see them go to a 30 or 35, something like that. That's what I would like to see, but it varies. What if they go down? That can happen too. And so that degree of variation over a period of time is what we're looking at as a standard of error. Now, your standard error of measurement is the standard deviation of the observed scores from the true score. So what's the difference from the observed score that you and I see and a true score, which would be a true measure of their ability? Is it the same? If it is, that's great. Because, as you see right here, the higher our standard error, the higher the reliability. As our SEM goes down, that means there's less reliability. Now, you must know the reliability coefficient to calculate the SEM. Remember, we talked about the reliability coefficients like when we were looking at 2 chapters ago about reliability. There's a Cochrane's and there was another one. We got to know the reliability coefficient of the test. Once we know that, we can calculate your standard error measure. But we want a reliable test that's going to generate a very, very good score for us. So, standard error of measurement, just one way to kind of tell just how reliable our tests are. So what in the world does all this mean, other than get us all confused? Well, first of all, there are many ways to define and interpret scores on a given test. We discussed a number of the ways to figure out the Z-score, T-score, standard error of the mean. Well, when it's all said and done, our tests are nothing more than a tool to help us measure people's ability, or they measure their knowledge. And so we want to be able to have the best tool that we can in order to get a very accurate and true idea of what they know. And that depends upon the reliability of our test and the validity of the test. So if we know the reliability of a test and be able to kind of measure it over a period of time, then we can also make some estimates of the standard error that's in our test. Now, do I expect each and every one of you to go out there and create a test and then start doing all these statistics on it? No. I've never done that on any of my tests, and I don't expect you to do it either. But it doesn't mean that it's not important for standardized tests, like the Compass, like the ACT, like the SAT test, where thousands and thousands and thousands of people are going to take that test over years to see whether or not these people know what they need to know in order to go to school. The California Achievement Test, same thing. The LEAP test. Let's face it, there are a lot of states right now that are looking at testing to see whether or not teachers are doing their jobs. They call it high stakes testing. Now, whether you agree with it or not, it's happening. And there are a lot of teachers throughout the United States right now that their salaries and their future employment depends on their students improving as they are testing. And there are a whole lot of people out there that are saying, no, this isn't what you need to do, because of the errors that these tests can have in them. And they're not perfect. So why are you placing all of this value on just some tests? Does this person get the raise because their students, improved by 5 points, and the next teacher doesn't get a raise because their students just their scores were just 2 points higher? Well, there's a whole lot of controversy that is associated with this type of testing. But the thing is, the test has to be reliable. And that's the important point.